Good day, ladies and gents, and welcome to this first video in my grade 10 mathematics series. Today we are going to have a look at our number system again, and we are going to expand on that number system and learn about rational numbers and irrational numbers. Alright, now you may be wondering, why do we need to know about rational numbers? Why do we need to know about irrational numbers? Why do we need to know about the number system at all? Well, it's very important. Now, if you think about mathematics as a language, you know, like the language that you and I speak with each other, then mathematics is sort of the language that mathematicians use to communicate with each other in maths, all right? Now, we use different words to deliver the message that we want to deliver, to speak to each other, to ask, you know, questions, give responses, and just have general conversations. And in mathematics, the words that we use are going to be our expressions, our functions, our terms, things like that. And what are those made up? Well, they are made up of numbers. So we must understand where our numbers come from if we want to understand how to apply them in this language of mathematics. If we want to be able to have decent mathematical conversations with each other. All right, now stick with me. It might not make sense to you right at this very moment, but as we go along this whole year in grade 10 and we learn about a whole new concepts like functions, and we learn about algebra, and we learn about a lot of new exciting things, it'll become more and more clear to you why we need to understand the types of numbers that we use, you know, our mathematical words, if you will, and how we use them. All right, so let's kick it off. Let's have a look at the number system. By now you should already be familiar with your natural numbers. And the symbol for our natural numbers looks like this. Alright? We can then expand upon this, and that'll give us our collection of whole numbers, which is our natural numbers with the zero collection added to that. And then we get negative numbers, and I mean, you should already be familiar with that by now. We get our negative numbers, and then when we expand with the negative numbers, we get our collection of integers. So now today we are going to expand on this, and we are going to divide our collection of integers into rational numbers. Rational numbers are denoted with the symbol Q. All right, and we give our Q a little double stripe there as well to indicate that it's a bolded part. And then also our irrational numbers, which looks more or less the same. It's just a Q with an apostrophe at the end. All right, so we are going to have a look at rational numbers and irrational numbers. Right, so let's jump on right in, and we'll begin with rational numbers. Now, it's not very difficult to understand what a rational number is. If you understand what an integer is, you will immediately understand what a rational number is. If we have a ratio A over B, and this ratio is such that both A and B are integers, all right? And one important distinction is that B is not equal to 0. Why? Because we cannot divide by 0. All right, dividing by 0 will make your brain explode. Okay, so be very careful. You cannot do that. Okay. All right, so we have a ratio A over B, and if that ratio can be expressed as any ratio of two integers, then this is called a rational number. All right, and remember our symbol Q for it. Okay, so let's have a look at some examples. Let's have a look at the fraction 1 over 2, which is also known as a half. All right, the numerator 1 is an integer. All right, do you agree with me? And the denominator, the one at the bottom, is 2. It's also an integer. So 1 over 2, this fraction right here, can or is at the moment expressed as a ratio between two integers, and therefore we can say that this is a rational number. All right, does it make sense? It's easy peasy, easy to understand. All right, let's have a look at another one. What about 3/7? Is this a rational number? Can you work it out? Okay, again, let's have a look. Remember now, the definition for a rational number is any ratio that can be expressed as a ratio between two integers. So our numerator, again, 3, is that an integer? Of course it is. And the 7, is that an integer, the denominator? Yes, that's also an integer. So 3 over 7 is in fact a rational number. Right, this is very easy. Okay, let's spice it up a little bit. Let's use a different example. What about negative 4 by 12? All right, negative 4 twelfths, or negative 4 by 12, or the ratio between negative 4 and 12. Is this a rational number? Okay, again, let's go and have a look. Remember now, what is the definition for a rational number? Any ratio that can be expressed as a ratio between two integers. Is negative 4 an integer? Do you know? Yes, of course, negative 4 is an integer. Why is it an integer? Because our collection of integers includes all negative numbers, 0, and all positive whole numbers. So negative 4, yes, indeed, negative 4 is an integer. What about 12? Of course, 12 is also an integer, and so we can say that our fraction, negative 4 over 12, is a rational number. All right. Now, okay, right. What is negative 4 over 12? You can take your calculator and we can calculate it. All right, so let's say negative 4 divided by 12, and that gives us a decimal number of negative 0,3333, and these 3's repeat into perpetuity. All right, we write it like this: negative 0,3, and we put a little dot over the 3 to indicate that the 3 keeps on repeating over and over and over and over and over again. So now my question was, is negative 4 over 12, is that a rational number? And we determined that yes, indeed, it was a rational number. Okay, so when we have a look at its decimal, which is negative 0.3, and the 0.3 repeats over and over and over again, that means that negative 0.3 that repeats must also be a rational number. All right, does it make sense? It's just the fraction that we calculated using our calculator to give us the decimal number. So negative 0.333333 up into the end of time is also a rational number. Okay, I hope this makes sense. Now let's look at one more. Actually, let's look at two more. What about the fraction 0 divided by 8? 0 divided by 8, or 0/8. Is that a rational number? Okay, let's look at it again. And I'll say it over and over again. What's the definition of a rational number? A ratio that can be expressed as any ratio between two integers. All right, is 0 an integer? Yes, 0 is an integer. Why? Because 0 is contained in our collection of integers. So 0 is an integer. All right. What about 8? Is 8 an integer? Yes, 8 is of course also an integer. So that means 0/8 or 0 by 8 is a rational number. All right. Now, just for interest's sake, what is 0 divided by 8? That is of course 0. And we determined that 0 by 8 is a rational number, so that means that the answer or the solution of 0 by 8, which is 0, is also a rational number. Okay, and then one last example. What about the number 11? Is 11 a rational number? Okay, now let us go back to the strict definition of what a rational number is. A ratio that can be expressed as a ratio between two integers. So how can I express 11 as a ratio between two integers? Okay, well now remember, 11 on its own can also be expressed as 11 by 1. 11 divided by 1. What is anything that, if you divide anything by 1, what is that answer? What is anything divided by 1? Well, 11 divided by 1 remains 11. Can you see? So you can express the number 11 as 11 by 1. 11 divided by 1. And now let's go and have a look at it again. We now have a ratio, all right? We have 11 ones, if you want. We have 11 by 1. It's a ratio between two integers. Well, is it? Let's see. Is 11 an integer? Of course, yes, it is. Is 1 an integer? Of course, yes. It is also an integer. So that means that this ratio is a rational number, and that then means that 11 is a rational number. Okay, does it make sense? Easy peasy. All right, so the important thing that you need to remember here is that a rational number is defined as a ratio which can be expressed as the ratio between two integers. Okay, now then, let's go and have a look at an irrational number. An irrational number. So what is an irrational number? Well, the definition for an irrational number is pretty self-explanatory. If a rational number is a ratio between integers, then an irrational number is not a ratio between integers. Okay, I know it's silly and I hope it makes sense. But an irrational number is a number that cannot be expressed as a ratio between integers. All right, it's a number that cannot be expressed as a ratio between integers. So now at this point you may be asking yourself, but okay, what does an irrational number look like? Okay, so let's go and have a look at some examples. All right, let's take the number which is expressed as the square root of 2. Right, let's go and have a look at the square root of 2. Now, if you take your calculator again and you calculate the square root of 2, let's do that, the square root of 2, then we get the following. This is equal to 1,4,1,4,2,1,3,5,6,2, and so on and so on and so on. My calculator just ran out of space. Okay, so let's have a look at this decimal portion of this number, this decimal portion. And now I want to compare it to the decimal number of a rational number. Okay, the decimal version of a rational number. And we actually did that. We did that right here. All right. We had taken the ratio -4 by 12 and we calculated that in decimal numbers. And then we got 0,3333333 and so on and so on and so forth into perpetuity. Okay, so let's do that again. Let's have, okay, instead of having -4 by 12, let's just have a +4 by 12. And we know now that is 0,33333, and so on and so on and so on and so forth until the end of time. What is the difference between this decimal number and this decimal number? Okay, there are two main differences. The first one is the decimal version of a rational number will be finite. Okay, what do I mean by that? Let's have a look at the number 1/2, or a half. Okay, we know now that a half is a rational number. We've calculated that before. And if we took 1 divided by 2 and we put it into our calculators, we get 0,5. All right. Now, what do I mean by it's finite? It stops. It stops right there. It stops after one decimal number. It stops after the 5. We don't have a case where we have 0,555555555 and so on and so on and so forth into perpetuity. It stops. It's only simply 0,5. All right? All right, let's choose another number. Let's choose an 8th, or 1/8, 1 by 8, 1 divided by 8, exactly how you want to say it. If we take a calculator and we calculated 1 by 8, it would give us 0,125. All right, again, have a careful look at this. You can see that the number ends after 3 decimals. All right, 1, 2, 3. So after the 5, the number ends, it stops. All right, it doesn't continue over and over and over again into perpetuity. All right, so that's the first one. That's very important to note. A rational number, the decimal portion of a rational number, may end after a couple of decimal numbers, numbers after the comma. So it's finite. But what in the case of a number that's not finite, a number that's infinite or continues infinitely after the decimal? And we already have a number like that, this one here. Right, we already calculated it. It's 4 by 12. So if you take your calculator again, you say 4 divided by 12, it gives you 0.333333, and it goes on forever and ever and ever. All right. Now, the difference between this decimal number, and this decimal number is obviously that the 0.33333 continues on and on and on into infinity. All right, but there's an important distinction. The 3 repeats. The 3 repeats all the time. So there's a pattern. There's a repeating pattern. Okay? Let's have a look at the decimal number 4 divided by 9. Let's calculate that one. All right, we'll say 4 divided by 9, and that gives us 0.444, and so on and so on and so on, again into perpetuity. Let's have a look at another one. Let's calculate 12 by 99. All right, and remember, 4 by 9 is a rational number. 12 by 99 is a rational number. How do we know that? Because it is expressed as a ratio between two integers. Okay, so let's calculate 12 by 99. 12 by 99. This gives us a little something different. Look at this. 0.12121212, and so on and so on and so on. Now, again, we have a case where we have decimal numbers into infinity. They just keep on repeating over and over and over again. But we have a repeating pattern. What is the pattern here? A 1 and a 2, 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 and so it's 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, on and on and on and on. Okay, so that's the second most important rule of a rational number. The first one is that the decimal ends, okay, the decimal is finite. The second one is when the decimal is not finite, if it keeps on repeating to infinity, there is a repeating pattern. In this case it was 3, 3, 3, 3, 3. Here we had 4, 4, 4, 4, 4, and in this one here we had 1, 2, 1, 2, 1, 2, 1, 2. Now it can be any repeating pattern, all right? We can have something like 0.123, 123, 123, 123, and so on and so on and so on. It's still a repeating pattern. Now, if you are given a decimal number and the decimal number stops, you immediately automatically know that it's a rational number. If you are given a decimal number and there's a repeating pattern, then you also already know that it's a rational number. Now we can come back to irrational numbers. What can you tell me about the decimal number that is the same as the square root of 2? What can you tell me about that? Does it end? No, it keeps on going into infinity all the way. All right, right up to the end of that, wherever that may be. Do we have a repeating pattern? Let's have a look. 4, 1, okay, there's another 4, but no, there's not another 1. It's now 2. And then it starts back at 1 again. 3, 5, 6, 2. All right, it does not seem like we have a repeating pattern here. All right, so an irrational number is a number that cannot be expressed as a ratio between two integers. And we have as an example the square root of 2. So how do we write the square root of 2 when we use our mathematical language? What do we do with it? Nothing. We just leave it as the square root of 2. And we move on to the next one. All right? When we speak with each other in our maths language, and I show you the square root of 2, just like that, not anything done to it or transformed into a decimal value or anything like that. If I just show you the square root of 2, then you know the square root of 2 is an irrational number. And this is the best way to express it, to show it, all right, to write it down. Okay, let's go and have a look at another example. I'm sure you are all familiar with the symbol pi. All right, now pi is a number and it has to do with the geometry of circles. All right, we'll get to that a little bit later. But if you take your calculator and you go and search for your symbol pi, all right, and you press the equal button, all right, with those of you who have got the newer Casio calculators, if you type pi, it's going to show you just a pi. So if you want to transform your pi into a decimal, you're going to have to find this key. It looks like this. All right, that's going to convert your number into a decimal number. So type in pi, press pi on your calculator, and then look for this button and press that button, and then you should get a decimal value of pi, or for pi, that's 3,141592654. All right, do I have that right? 141592654. Okay, now let's have a look at this decimal number again. Does it end? No, keeps on going up until the end of time. Okay, and do we have a pattern? Let's see if we can find a pattern. 1, 4, okay, we've got a 1, but okay, no, there we have a 5 again. Okay, so the pattern is broken. If it's only broken once, there's no pattern. Okay, so you don't have to search any further than the first point where the pattern is broken. Okay, 2, 6, 5, 4. All right, so no pattern. There is no pattern in this number. So the number pi, all right, is also an irrational number, and this is its symbol. All right, a Q with an apostrophe, just like we showed that the square root of 2 is also Q with an apostrophe. Okay, so we said that our collection of integers, remember now this is the symbol for integers, okay, right? So our collection of integers is all the negative numbers from negative infinity. It includes 0, and then it goes on all the way to infinity, all right, on the positive side. So all the whole numbers from negative infinity and 0 and up to positive infinity. So that is all our integers. That collection contains all of our integers. All right. So now we say a rational number with its symbol Q is any number that can be expressed as a ratio of 2 integers. So that means the numerator must be an integer, the denominator must be an integer. And very, very, very important, in this case, the denominator may not be equal to 0. And why is that? That is because we cannot divide by 0. Now, ladies and gents, I would urge you to begin to remember this little rule here. This little rule here is very important. I'm going to keep on hammering on this little rule here up until the end of your schooling days. Okay, so that's very important. You must remember that when you are working with fractions or ratios, the denominator may not be equal to 0 because you cannot divide by 0. Okay, you're going to create a black hole and suck all of us in the whole world up into that hole with you. Okay, so again, the definition for a rational number is any number that can be expressed as a ratio between 2 integers. Okay, and then an irrational number is a number that cannot be expressed as a ratio between 2 integers. And examples of that, what we looked at, had been the square root of 2 and also pi. Okay, I hope it makes sense. Thank you very much for joining me today for this lesson. If there are any questions that you have, please use the comment section below. You can ask me your question and I will do my best to get back to you and to answer that. Thank you very much for joining me today. I hope all of you have got a lovely day ahead of you, and I will see you again in the next lesson. Till then, goodbye.